Let me start by thanking Rakesh, who's here, for inviting me here. And it's very nice to be in this beautiful campus. And so I'm basically going to talk about, so I was not very clear what exactly to talk about because the topics in the conference are essentially the entire universe. But I decided I'll go slightly on the macro side of quantum. So this is basically, as you will see, this is basically a talk about various aspects of, let's say, black hole information paradox, you could say that, and why the horizon plays such an important role. Hopefully it will become clear as we go along. And this is mostly work done with my students and postdocs that we had at ISc Suchetan, and my students Vaibhav, an undergraduate student Vaishnav, and my current PhD student Pradipta. So it's kind of like we have gotten farther than what I'm presenting here, but this is like stuff from about maybe a year and a half ago. But I thought it's kind of like a good opportunity for me to also review where we were. So please ask questions. I don't have to necessarily get to the end of the talk. So that's as far as I go. Okay, so I'll start with this statement. So the idea is that we are interested in understanding black holes. So black holes are often called the hydrogen atom of quantum gravity. So the idea being that back in the day when people were trying to understand quantum mechanics, the hydrogen atom was a useful system for them to try and understand, where they could cut their teeth. And black holes are one such thing for us when we are trying to understand quantum aspects of gravity. Okay, so quantum gravity, as you know, is depending on who you ask, it's a solved problem or maybe not solved at all. But either way, in order to understand quantum gravity, it is essentially it's perfectly clear. It's very clear that we will need to understand black holes as quantum objects. Okay, so this is that's one of the primary reasons I will be interested in black holes in this talk. So they're not interesting as astrophysical objects, but they're interesting for me, and I mean, at least for this talk, and they're really useful as a tool for understanding what quantum gravity might be. Okay, so that's the real reason. And black holes have a surface called the horizon, and it is known from a very long time that it's natural to attribute entropy to that surface. Okay, so if you have the surface of the black hole is basically what one calls the horizon, and the horizons carry an entropy. And the reason that is surprising is because typically when you have a region of space, you expect that the entropy goes as the volume of that space. And this is what we are familiar with in the statistical mechanics, in standard condensed matter physics or even field theory. That's what we expect. But that's not what happens when there is a black hole in the system. And we believe that it is a general property of gravity in general, that if you have a gravitating system, which is also quantum mechanical, we expect that the entropy might ultimately scale only as the area of the region and not as the volume of it. So this means, basically what it means for a black hole is that whenever you have a black hole, it comes with some unaccounted for entropy. Entropy, in some way of characterizing it, is basically our lack of fine-grained information, lack of detailed information about a system. So which means that whenever you say that a black hole has this much thermodynamic entropy, it means that it necessarily is not a pure state, at least the way we are looking at it. Okay, so that's right. Yeah, that's not like area. It's gravitating. So the point is that when you have a gravitating system, the entropy is bounded by the area. So, and the point in some sense is that because GH cross is sufficiently small, this is a very huge number. So a star's entropy, before it collapses, is actually much smaller than this. So once it forms by collapse and forms a black hole, its entropy will actually increase. And entropy is, even though it scales as area, because of this GH cross, which is a small number, it will become very large. So this is the idea. So yes, so the horizon, so as I was saying, whenever you have a horizon, a black hole horizon is part of the description of a system, there is no way to avoid having this unaccounted for entropy. So you have to have this sort of what seems like, so when you form a black hole from what initially seemed like a pure state in quantum mechanics, and you form a black hole, one needs to explain how exactly is this entropy explained. Okay, so because it's typically when you evolve a system and you know everything about the system, it keeps evolving. Finally, also, if you know everything about the system, its entropy is zero, because a pure state has entropy zero. So typically, it's a loss of information detailed information about the system that results in the production of entropy. But when a black hole forms, we don't have an understanding of how that happens because of various facts related to general relativity. Okay, so because, for instance, in general relativity, black hole solutions are described by very few numbers. So, for instance, a black hole that is rotating is essentially is completely described by its mass and angular momentum, which means that you cannot have a statistical mechanics count like you would have for a gas in a room coming from just counting the degrees of freedom of a black hole. Because according to general relativity, black holes are extremely simple systems. They don't have any degrees of freedom except the macroscopic charges that they have. So which means that where does this entropy come from is unclear. Okay, but we have very good reasons to think that black holes do have entropy. So this is a problem at some level for classical general relativity. So the horizon of a black hole is basically the general relativistic description of the surface of a horizon. So since it contains unaccounted for entropy, if you want to have a microscopic quantum mechanical description of a black hole, you necessarily have to sacrifice the notion of a horizon. Okay, so this slide, by this last statement I'm making is, even though it's not, the way I have presented it, it seems almost inevitable, but I wouldn't say that it is a fully widely, there are many people who might disagree with it, so but I think the way I am stating it here, it almost seems like unavoidable, to me at least, that if you have a black hole microstate, it must necessarily not have a horizon. Because if you have a horizon, it comes with entropy in general relativity. Okay, so the point of this is that understanding the bulk microstates means the microstates of a black hole, seems essential for a satisfying resolution of the information paradox. And the information paradox is essentially what I stated earlier. At least one version of it is what I stated earlier, that if you form a black hole from pure state, from some quantum mechanical pure state, why does it evolve into a state which has entropy? So we don't seem to have so you might ask the same question when you form, like, when you have a, when you have like a burning piece of coal, let's say. So that initially when you start the system, let's say somehow you have an understanding of what the initial state is, but eventually it becomes, everything heats up and becomes thermal, and there is entropy associated to it. But that is associated to the fact that we don't keep track of all the information. But in the case of black holes, the problem is that we don't know what information we could possibly keep track of, because general relativity says that there is only this much degrees of freedom associated to a black hole, which is basically just two numbers, mass and angular momentum. Okay, so that's the base. That's a sort of one version of the information paradox. And it's a Lorentzian problem in the sense that, like, my talk will get the first slides, I'm kind of aiming it also as general audience and students, but it might get a little technical as we go. So information paradox is a Lorentzian problem. And the reason, what it means to say that it is a Lorentzian problem is that you want to frame it in terms of a genuine, honest to God horizon in space-time. Okay, so it's not sufficient. You cannot answer this question very easily in Euclidean signature, where usually the Euclidean gravity is formulated. And so the reason for that is that Euclidean pictures oftentimes are more thermodynamic than statistical mechanical. That's one way to understand it. So unfortunately, we have currently no top-down construction of a typical finite temperature black hole microstate in any theory for that matter, and in particular in string theory, which is roughly the setting in which I'll talk about. Okay, I won't necessarily need many aspects of string theory. As you'll see, my talk is very pedestrian in some ways. But the general idea, so the problem that we have is that for typical finite temperature black holes, we do not seem to have any description of them in any so-called theories of quantum gravity. Sure, absolutely.
Suppose if you take three-dimensional gravity.
Yeah.
You have BTC black hole.
Right.
You have horizon there.
Yeah.
And there is no information paradox problem there.
Why is that?
Where is it? There is not, because gravity in three-dimensional is non-dynamical. There is nothing to...
No, but I think that's a puzzle nonetheless, right? Because you have to explain. So this is one reason why you might say that the Chern-Simons formulation of gravity in 3 dimensions is not the full story. Because if you had...
No, I don't even go to...
Fine, right, yeah.
Stay completely in gravity.
Yeah, but I'm saying that one version of your statement that there is gravity has no propagating degrees of freedom in 3 dimensions is the statement that gravity can be formulated as a Chern-Simons theory. Because it's essentially a topological. Chern-Simons theory doesn't have local degrees of freedom, etc., etc.
Topological is independent of whether you can formulate it in Chern-Simons.
I'm just saying that. I'm saying that it's one version of that statement.
There is no
Yeah.
degree of freedom in
Yes. Yeah, I'm saying that it's a manifestation of that is also the fact that Chern-Simons formulation exists. Right.
Chern-Simons formulation may not be may not completely
Yes,
describe that.
but I'm saying I'm giving you an argument why it is not the case that there is an argument for why it is not complete is the existence of, let's say, BTC black hole, because BTC black hole comes with an enormous amount of entropy. So which means that a topological theory may not carry all the full information about the Hilbert space. So that's one way to one problem with this thing. So I wouldn't say that there is no. In fact, I would say that there is information paradox in 3 dimensions even in ADS. So I mean, there are multiple versions of it. For instance, you could phrase information paradox not necessarily just as the formation and evaporation of a black hole. You could also frame it as a question about the status of the smoothness of the horizon after an order S time scale. So that's the way in which I would phrase it here. Because if you have a large enough BTC black hole in ADS3, it will not evaporate. But there still is a version of the information paradox which is related to the question of what exactly a smooth horizon means in this thing. So yeah, so the information paradox, I would say that anytime there is a horizon and a localized black hole, there is some version of the information paradox. And in fact, there is a converse statement also. I don't know if there is a proof of it, but I believe is that the only place where you have information paradox of the kind that we are interested in is when there is a horizon. So the horizons are very crucially tied to the existence of information paradox type things. I mean, if you rule out cosmological horizons, let's say. So yeah, so I mean, yeah.
Why do you say finite temperature black holes?
Because in the string theory, we do have microstates for 0 temperature black holes of certain kinds. But that's not, so they address some aspects of the information paradox, but not the ones which are most directly related to, for instance, late time behavior. Like for instance, things related to evaporating black holes. Okay. So there are aspects of the problem which are related to late times. So it's not clear from what I said that there is an aspect of that kind, but it is a fact nonetheless that, like for instance, old black holes. Old means old in when you have G Newton is some small number, time scales which are much higher than, let's say, 1 over G Newton, right? In those time scales, you expect that some version of the information paradox should kick in. So those questions, those microstates in string theory, which are for 0 temperature, at least it's not easy to, I don't think there is a good formulation of the question there. So that's the issue. Okay, so there is string, as Rakesh was saying, there are examples of microstates in string theory. Microstates means just like you have a gas of molecules here. So if you want to describe it using temperature, pressure, and so on, that's a macroscopic description. Okay, but if you want to describe it using all the momenta and velocity of each individual particle here, let's say in some statistical mechanics type description, that's a microstate of the gas in this room. Similarly, for a black hole, we only have the macroscopic description, it seems like, which basically captures the mass of the black hole and, let's say, the angular momentum of the black hole. And if you're looking at a non-rotating black hole, it's just the mass of the black hole. So in those cases, what is the microstate of the black hole is what we are trying to understand. So in the case of this, so these are some words. I mean, so there are certain classes of 0 temperature black holes where string theory has made progress in understanding this. And so yeah, I mean, I can just skip this slide. It's not very important. So these statements, the punchline is that, as I was answering, at finite temperature questions about black holes, these microstates are not immediately useful. That's the punchline. The rest of it you can ignore. So given the state of affairs, right? Given this state of affairs, we can ask, can we engineer an instructive picture of a bulk microstate using bottom-up arguments? Because the point is that, so in any known theory of quantum gravity, we don't seem to have a controllable construction of a microstate in the quantum gravity. Okay, so for instance, in string theory, as we discussed, you can construct certain microstates in the 0 temperature case in some cases, but it is not sufficient to answer this question of finite temperature, guys. So is there a way in which we can motivate a structure or a picture of a microstate in the case of black holes in finite temperature quantum, finite temperature setting? So roughly the picture would be that, I mean, it's like we don't understand. Let's say back in Boltzmann was thinking about microstates for gases in this room. He did not have access to the standard model, which is really the truly UV complete theory from the perspective of, let's say, if you ignore gravity, that's the UV complete, ultraviolet complete, complete description of physics in this room. But he did not have access to that. But he nonetheless had a useful model for a microstate of a black hole, because he made up this model that, okay, every gases are basically made of spheres or whatever, that kind of thing. So that can be thought of as a model for a UV complete, description for a microstate of the gas. And it turned out to be useful. Okay, it taught us many things. And so something like that is what we are trying to look for here. We don't have access to the full UV complete final theory of quantum gravity, but can we come up with a model for a microstate of a black hole which can be instructive and which we can test and check whether it leads to reasonable conclusions about low energy physics. So this is the setup. So this is what we mean by, essentially what we can think of it as a bottom-up approach to black hole microstates. And so the possible demands that one can make, the first and zeroth order one is that we want to work in Lorentzian signature. So Lorentzian signature means that there is an actual physical time in the problem, because we are interested in understanding physical black holes and not just the thermodynamic aspects of it, which are usually captured by Euclidean black holes. Okay, so if Euclidean signature black holes are useful for understanding thermodynamics, but they're not really useful oftentimes for understanding statistical mechanics. So we want to work away from this extremality. So extremality is another way of saying that the black hole is zero temperature. Supersymmetry is a further refinement of extremality. So we want to stay away from it, because those are things which are special to special classes of black holes, and we are interested in questions which are generic to quantum gravity. So we have some intuition for bulk states in ADS-CFT. So ADS-CFT correspondence is our current functioning sort of theory of quantum gravity. So in certain classes of spacetimes where there is a negative cosmological constant, so as you know, there is, you can work with the universe. You can consider universes with positive cosmological constant, zero cosmological constant, or negative cosmological constant. This is from the point of view of a theory, at least as we understand it, it just seems like an arbitrary choice in some sense. Okay, but so the case that is physically what seems to be interesting is the case with positive cosmological constant. But because our universe is accelerating. But in general, we think that maybe even if the cosmological constant is positive, we might learn something about the universe by considering cosmological constants which are zero or negative. And zero has a great historical precedent, which is that we work with quantum field theory, which is we work with the zero cosmological constant, and we have learned so much about the standard model. So cosmological constant may not be significant for some questions, and I will argue that for some questions in quantum gravity, like information paradox, the sign of the cosmological constant being negative is also not a problem, because we'll still have the same contradictions that we have in flat space or in cosmology when dealing with black holes, even when the cosmological constant is negative. And so if we can find a solution to this problem in the setting of negative cosmological constant, that is still teaching us something about the questions that we're interested in. So that's what ADS-CFT is. ADS-CFT is basically a picture for a quantum theory of gravity in universes with a negative cosmological constant. And this is some place where we expect that we understand quite a bit about gravity. And in fact, I would say probably that that's the most that's one piece of physics that has come out from string theory, which may have some chance of lasting. So many things that we have learned about in string theory, various things people construct, particle physics models, and so on. So how much of that will stay the test of time remains to be seen. But I think if I had to bet on one thing that will come out of string theory which has lasting value for quantum gravity, that will be the ADS-CFT correspondence, or sometimes also called holography. Okay, so for starters, it's also final ingredient that I will demand is that for starters, it seems reasonable to try and understand the black hole itself and not treat it as an open system. Okay, so that's the fourth ingredient, which is basically the statement that I want to avoid black holes whose size is much smaller than the curvature scale of ADS. Okay, so if the black hole is much smaller than the curvature scale of ADS, that means that it's actually effectively that black hole is living in flat space, so it will evaporate away. And that's something that actually, as a first thing, I don't want to deal with that. I want to keep the black hole at finite temperature, but I don't want it to evaporate away because it leads to extra technical complications. Okay, so these are the four requirements that I'll have. And so this is the setting of what is called the large ADS black hole. So let me draw a picture of ADS. So ADS is usually drawn as some kind of a cylinder. So you can think of ADS. ADS is quantum gravity with negative cosmological constant. And so you roughly think of this ADS as basically kind of a box for containing gravity. It's not a too bad way of thinking about the geometry. So in flat space, for instance, the universe, the gravity doesn't have a box; it just leaks off. But here, on the other hand, we have a sense in which we can contain gravity in a box. And the black holes that I'm interested in are basically big black holes in the box. So if you put a small black hole here, it will evaporate away into radiation. And I don't want that. I want it to make it big so that the radiation that comes out of the black hole reflects from the boundary and the black hole can be in equilibrium with itself. Okay, so this is a useful tool to understand black holes in ADS. And I have to say that this system was first studied by Hawking and Page back in 1970s, long before the ADS CFT correspondence. Okay, so this is our setup. So we can our first natural target is to try and get a bulk picture of a heavy microstate. So by a heavy microstate, I mean a black hole of this kind. I'm interested in understanding how can you model microstates for a black hole if the black hole is big and heavy. Okay, so this is the question that I want to answer. And what can be a bottom-up way to engineer a heavy CFT microstate? So in ADS CFT correspondence, the statement is that quantum gravity in this bulk of this ADS cylinder, inside the ADS cylinder, there is gravity. So, but this can be described using some non-gravitational, completely conventional quantum field theory living on the boundary of that cylinder. So that's the claim of ADS CFT correspondence. And so if you want to understand black hole microstates here, what you really need to give me is I need to tell you what the states of the conformal field theory on the boundary are, which are dual to my black holes that are sitting in the bulk. So this is the setup. Okay, so the question is, and that is a very difficult problem because typically the conformal field theories which are dual to gravity are strongly coupled, and we don't know how to solve strongly coupled theories very well. So that's one reason why we want to that's one of the reasons why we want to have like a bottom-up model for these microstates. Okay, so I'll explain what bottom-up means. So the first question one might ask is, should we completely give up the metric? Okay, so if you have a space-time which is there is a black hole sitting in this geometry, for instance, if you are familiar with the Schwarzschild metric. So there is a metric, and how much of that metric picture should one give up if you want to have a microstate picture? So this is the question. So at zeroth order, at a very basic level, you might imagine that if you want to have a quantum gravity, everything may become discrete, and the space-time picture completely breaks down. So this is always a possibility. But on the other hand, there are reasons to think that in order to understand the issues related to black hole information paradox, such a drastic thing may not be necessary. We can probably understand the physics of microstates of black holes without entirely sacrificing the metric. In particular, so what I'm saying here is basically that so finite n basically means finite g Newton. So when the Newton's constant is finite, we expect that the space-time is we don't know exactly what happens, but we suspect that space-time might become grainy in some sense and quantized, and we don't understand how to do things there. So, but the metric that in Einstein's gravity is useful is in many situations, and we know that the metric doesn't by itself lead to the unaccounted for entropy. So, for instance, in this region of space that we have here, which is Minkowski space, the space metric description is perfectly valid, but we don't have unaccounted entropy. So we expect that this could very well be approximately be describing some state without an entropy. Okay, so because of which it's not clear that just because of the metric description you might run into trouble with having a microstate picture of a black hole, but it is so what we will try to do is that, but the horizon is what is actually giving rise to this unaccounted entropy. So that's what we would really like to give up. So such ideas have been around for a long time and go by various names in various contexts. Sometimes they're called brick wall at the horizon. So what the idea is that what happens if you just cut out the region right outside the black hole and you only look at the region outside of a black hole. So these ideas have been there for a while, and so this is considered as a radical departure from classical general relativity, because classical general relativity tells us that if somebody falls into a black hole, you just fall through straight. Okay, so and there is by no local experiment you can distinguish the fact that there is something happening at the horizon. So for instance, if there was a sufficiently big black hole, we could be passing through the horizon of a black hole and not be able to detect it. So this is something that it's just expected in general relativity, and this is part of the principle of equivalence that led Einstein to his theory. So that's what this is. So this is but on the other hand, people have tried doing things of this nature, And giving up the metric everywhere is a type of entire space-time is, on fire suggestion. But the horizon, if you just leave the horizon out, that is a little bit like, the structure of the only the horizon is, we are making it, depart from general relativistic expectation. So this is, as I was saying, this is radical because it's a direct apparent violation of the principle of equivalence. So the question that is our focus, is there a way to give up only the horizon in a way that we can salvage the principle of equivalence in some suitable limit? Okay. So let's say that you're putting in a cutoff, and are there at least some signatures of the principle of equivalence that we can retain, even though we have this sharp cutoff outside the horizon? And so a key starting point for us, whenever the people have discussions of this type, oftentimes there is this implicit idea that if you put a cutoff around the black hole, so you are violating a principle of equivalence all through. But the real question that one should address is that even if you put a cutoff, if low energy correlators in the theory look identical to that of standard smooth horizon bulk effective field theory, then this is still not a violation of principle of equivalence, because principle of equivalence is not a UV complete statement. It's only a statement of bulk effective field theory. So it's a low energy correlation functions which are supposed to satisfy these the principle of equivalence. And so if the UV complete correlators can look like bulk EFT correlators, let's say up to some suppressed power in the Planck's constant, then the equivalence principle is salvaged in the bulk EFT. So this is what we are trying to aim towards. So yeah, let me say a few words in case these words are a little this thing. So bulk EFT is just a name for general relativity plus field theory living in space-time, and it's viewed as a low energy effective description. So we'll largely be agnostic about the UV completion. So what that means is we are not going to try and say whether, because we are primarily interested in constructing a bottom-up model for black hole microstates, we can be agnostic about what the UV complete theory is. In particular, in no theory do we know to explicitly construct these microstates. So fuzzballs, so fuzzballs are a name for efforts of this kind to construct. So let me just skip this slide. So yeah, what we are trying to construct is essentially a bulk Hilbert space where the correlator computation. So you have a stretched horizon, or we have a cutoff right outside the black hole, and we are going to try and go to do quantum field theory in this background. And then we will ask the question of what kind of correlators can reproduce the conventional expectations of a smooth horizon. So this is what we are trying to do. So a key hint is that the stretched horizon, or the stretched horizon is the region where I'm cutting off. So the basic picture is that you have a black hole, and the main picture in all of these things that is emerging seems to be that you remove a region outside of the black hole, about a Planck length or so outside of the black hole, and then you look for correlation function calculations in this setup. And what we are trying to do is to see whether how much do these correlation functions away from the black hole depart from the smooth horizon or the bulk EFT expectations. This is what we want to understand. So the point is that so this is the point of the stretched horizon. Stretched horizon is essentially the place where we are putting this cutoff, and so it's a parameterization of our lack of knowledge of the UV completion. So it really should be thought of in some sense like a regulator in quantum field theory. And if this picture is correct, we should be able to find a proposal where the correlators computed with the stretched horizon look like smooth horizon correlators up to exponentially small corrections. This is what our punchline would be eventually. Okay, so the claim is that if you membrane paradigm, one has to, so stretched horizon, membrane paradigm, fuzzballs, all of them are roughly similar ideas. So the question is, how should one set up the correlator calculation in a membrane paradigm so that this question has a well-defined answer? So that's what we are trying to do. So yes, conceptually they are very closely related, because stretched horizon is really sort of like a membrane paradigm. So stretched horizon, brick wall, all of those things are from 1970s. We are, like as I was saying, the first idea that was there was from Toft long ago. So yes, you're absolutely correct. So it's you could think of it as a sort of a how do we attribute physics to the membrane? That's one way to ask the question. So right. So yes. So two more hints that I'll take is that, So one of the problems, people never liked, one of the reasons why people did not like this idea of cutting off things right before the horizon, one of them is the principle of equivalence being violated. And the second reason, which is more sort of mundane, is that if you cut off the black hole horizon, the horizon is obviously gone. And what you are left with is basically a system with really no temperature, no natural temperature associated with it. Because the presence of the horizon was fundamental for Hawking's calculation of getting the Hawking temperature. So if you remove the horizon and cut it off, then there is no notion of a temperature that you can attribute to the black hole. So that's one problem. So it's just removing the horizon by ad hoc. It removes this issue of various issues related to information paradox, but it also comes with a heavy price. One of them is the violation of principle of equivalence, and the other one is that you don't get the successes of Hawking's calculation. So you immediately lose all of them. And the second thing is that, like, this is a manifestation again of the principle of equivalence, which is that if you cut off a surface right outside the horizon, like Tooft did, and this is one reason why Tooft himself departed from it eventually. So is that what you find is that there is a negative stress tensor at the horizon. Okay, so there is a negative divergence of stress tensor at the horizon if you just ad hoc cut off the thing and compute your expectation values, okay, of the quantum field living there. And this is sometimes called, this choice of sort of boundary conditions, if you like, can be thought of, is sometimes called the Boole-Ware vacuum. So the Boole-Ware vacuum, or the natural state that emerges if you just cut off the exterior, they cut off the black hole right outside the horizon, has this property that it comes with a huge negative stress tensor flux, essentially a divergent stress tensor flux. And this can be viewed essentially as the Einstein penalty. So that if you cut off, if you remove, essentially the stress horizon is some object that is staying right outside the horizon. Okay. So, and if you keep that, in order to keep that there, you need to expend energy because the black hole is trying to pull everything in. So if you are trying to pull everything in, then and you want to keep the stress horizon right at the horizon, then you have to pay an energetic price for it. And that's essentially what this negative stress tensor is telling you. Okay, so there are both of these are sort of substantial problems in the sense that you put something outside the black hole and you claim that you lost everything in some sense by doing this because the black hole's essential properties are all gone. Okay, so both the classical properties which are related to its equivalence principle as well as its quantum properties which are related to Hawking's calculation. So what have we really accomplished by it? So the one thing that we have accomplished is that we have if you do this immediately, you can hope to have unitarity in the sense of standard quantum mechanics be preserved. Because the moment you have a horizon, that's the origin of all things related to information paradox, because precisely this thermal aspect of the spectrum that emerges is what is responsible ultimately for the information paradox. So we have hope of retaining unitarity. One second, but we have hope of retaining unitarity, but we have lost all the successes of black hole physics, both in classical and quantum field theory in curved space. Yeah, please go ahead.
Maybe you can say a little bit about what you mean by violating the principle of equivalence, because normally when you think of principle of equivalence, say is phrased as gravitational mass is equal to inertial mass.
Yeah.
Or maybe.
Yeah, I mean, what I mean by principle of equivalence is so gravitational mass is inertial mass is sort of the statement that like you could also frame it as the statement that locally in a gravitational field you can go to a coordinate system where you are in free fall. So right? Yeah. Yeah, that's what I mean.
Is that there always exists a local inertial frame.
That's right.
Which,
yeah.
Metric looks like eta.
Yeah.
First derivative 0.
That's right.
Not necessarily.
That's right. That's exactly.
That
That's what I mean. Yeah. So I mean that it's basically the idea is that the horizon is a generic point in space-time. So if it's a generic point in space-time, unlike at a singularity or something, you expect that you can go to a coordinate frame where the metric is locally flat. So for instance,
may get violated.
So for instance, if I'm putting a stretched horizon, see the stretched horizon is so because if I'm putting a stretched horizon right outside the black hole, it's not, even though the black hole looks like a sphere and all that, it's actually I'm doing work in order to keep it there, right? Because the black hole is trying to pull it in. So there is an automatic acceleration there, and that's what I need to compensate, which is sort of the QFT in curved space manifestation of what you just said, which is that, So so these are the main problems, and these are serious problems, and that's the reason why people have not been, but I should also say that in one of the reasons why you might think that this might not be the whole story is because there exists some particular solutions in string theory. Like, okay, let me backtrack a second. So This you can also frame these statements as manifestations of what is called the no-hair theorem in general relativity, which is that if you have a black hole, as I was saying earlier, it's basically described by a very few number of parameters. So for instance, a black hole that is not rotating or charged, it just, if you specify its mass, the black hole is completely specified. The black hole solution of general relativity is completely specified. And that's related to the fact that you cannot do any kind of dressing at the horizon. The horizon doesn't have any structure. It's not like the surface of a star where the details can differ. So every black hole at the horizon looks identical is one of the predictions of general relativity, if once the mass is given. So this is related to this no-hair theorem that I was saying. So, but we know, so if you could dress the black hole with microstates, some structure at the horizon, then in principle, you could evade this no-hair theorem, and that could give you a statistical mechanics picture of what the microstates could be. Yes, but that's in zero temperature. That's right. So I'm just coming to that 1 second. So what I'm saying is that even though this statement I made here is both of these are, definitely true statements, at least as we understand it, we also know that in a UV complete setting like string theory, there exist solutions where actually there are, zero temperature case, not in finite temperature case, but at least in those cases, we do have solutions which give structure at the horizon. Okay, so this is a second. So you should somehow suspect that maybe this is not the whole story. Yeah.
Don't simply cut off the horizon.
Yeah.
Something close to stretch horizon.
Yeah.
One can change the boundary conditions.
Right.
Of the fields outside.
You mean at the stretch horizon?
Yeah.
Okay.
Outside.
Yeah.
Like say Robin boundary.
Yeah. Sure. Yeah.
That can produce.
Yeah. So the
freedom very close to the.
That's right. So what we will, in fact, anyway, I will work with Dirichlet boundary conditions, but we know that any boundary condition, as long as it is not dissipated, in the sense that it is not infalling, so then the state, it's irrelevant for whatever boundary condition you choose. The construction that I'll show you will basically give you, correlators which are consistent with that of a smooth horizon. This is what the punchline would be. So, and you will see why that is. As maybe you can ask the question one more time if my answer doesn't, completely address it. So the point is that, but it is important that the boundary conditions that we are demanding at the stretch horizon are not dissipated, in the sense that they're not, for instance, infalling boundary conditions. Because if they're infalling boundary conditions, they're essentially, that immediately leads in some form or the other to unitarity violation. Essentially because.
As long as the Hamiltonian is self-adjoint.
Yeah.
That can be a problem.
Even so, the Hamiltonian.
Those boundary conditions, is the Hamiltonian self-adjoint or not?
So yeah, I mean it's.
And,
Yes, I mean it'll always be self-adjoint because it's just Dirichlet boundary conditions. Okay, in the thing that I'm working with, there'll always be Dirichlet boundary conditions with standard quantum field theory in the bulk. So they will always be,
That doesn't have singularity problems because Dirichlet is going to demand it is zero there.
Zero means, I mean the field. So these are boundary conditions for the modes in the quantum field theory. Like these are basically standing modes of the scalar field, let's say, and I can quantize it. And there are issues related to, like, if you want to. So if you wanted to have a stretched horizon in the full UV complete theory, I think these things will violate locality, causality, various things. And the reason is that these are, what you basically have is a cutoff, right, in space-time. But the point we will make is that this should really be thought of as an analog of a cutoff, for instance, in quantum field theory, which also violates, let's say, things like unitarity, for instance, Lorentz invariance is broken by lattice and so on and so forth. So, but on the other hand, we expect that the infrared observables still satisfy all the properties, all the good properties of quantum field theory that we expect. So so the stretched horizon is truly an ad hoc object. I really want to emphasize that. So, but the point is whether low energy or, low point correlators in, which are low energy observables, do they basically lead to differences from what we expect from, standard smooth horizon physics? That's the question that we are after. And the answer ultimately would be no, it's still not, you cannot detect it. So that's the reason why I view this as a regulator, actually. I don't view it as, it's a proxy for our ignorance about what the genuine UV completion is. And fuzzballs are kind of like an example that we know, where at zero temperature, at least, we seem to have some, regular constructions in full string theory.
So the stretched horizon is just a little bit outside.
That's right.
Okay, so you put the stretched horizon, let's say you put Dirichlet boundary conditions.
That's right.
And while you are doing your calculation, your friend mischievously replaced the horizon by the black hole by an ordinary star.
Yeah.
So,
I will know the difference. I will know the difference.
You will-
I will know the difference. Yeah. Because the point is, it is very important that the stretched horizon is about a Planck or string length away from the horizon. So if it is not, actually the normal mode structure of that I'll see outside the black hole will change. So this is actually, that will be very crucial.
you can't tell whether-
Yes, yes. So for instance, if you put a generic cutoff somewhere, this is essentially Planck's calculation, right? So if it's essentially like a cavity in which you have some boundary conditions, the boundary conditions are fundamentally irrelevant as we, for the systems which are sufficiently high energy, the boundary conditions are not really, we put periodic boundary conditions, we put various things we put. So ultimately, but on the other hand, Planck's radiation law is sort of independent of that. So it's roughly a similar idea. But the crucial thing is that because of the cutoff is near the horizon, the redshift at the horizon will play an important role in controlling the horizon. And that's, I think, the one technical fact. I think, thanks for asking. I'll say that again, but it is one technical fact which makes a huge difference for various things compared to, let's say, Planck's calculation. Yeah, so this is one paper that, which is not very highly cited among the various papers that are there in this sort of thing. So, but it's which we found very inspiring. So what they suggested was that if you want to have, get rid of this problem, that this divergent stress tensor here at the stretched horizon, what one should do is basically you should cover the stretched horizon with a huge amount of radiation. So you let some radiation at basically the Hawking temperature, essentially. If you do that, I mean, Hawking temperature is measured from infinity. So if you do that, what you will find is that, okay, you are sort of zeroth order kill this problem, okay? So it's crucial that it is a negative stress tensor. So you have a chance of adding matter or energy to the system and make things well defined. So what is remarkable about both these problems have the same solution. This is one thing that I think, I don't know whether people are really emphasizing, but this was one of the key points that we found very sort of useful in thinking about it. So what the idea is basically that once you remove the stressed horizon, the problem is that the system is not at finite temperature. So, but if you put radiation on it, it will automatically make it, well defined, and you have a thermal system and all of the features. I mean, not all of the features. You will see that we have to do more work to make it better. But at least this idea of dressing a stretched horizon with a radiation is something that is natural to work with. So what we are going to do, and now I basically come to the sort of the punchline or the main prescription that we have for what a microstate in the bottom-up approach to what a black hole microstate might look like, is that interpret this radiation, the radiation that Israel and Mukoyama were, they've had a radiation fluid with some stress tensor and so on. So, but instead of interpreting it as a classical fluid, what one should do is one should just quantize fields with this Dirichlet boundary condition and look at excited states of the quantum field theory at the black hole mass. Okay, so that's what our prescription would be. And that basically, you don't have to have this fluid as an ad hoc input. We are just looking at states in the Hilbert space of quantum field theory with a stretched horizon, but at the black hole mass. Okay, and this is very naturally a model for microstates because it is, when you specify, you're essentially specifying an ensemble. So if you did not put the stretched horizon near the black hole's horizon, and instead you did this calculation in this room where there was a wall there and a wall there, what you would rediscover is Planck's calculation. But instead, what we are doing is we are putting a stretched horizon around here, and then this box, we are quantizing our scalar field, quantizing our field, whichever field, doesn't matter. So, and if you do that, you will basically get a Hilbert space of quantum field theory outside the horizon. And then we look at highly excited states. And it's interesting that the highly excited state is a worthwhile thing to do precisely because of the negative divergence in the stress tensor. Because otherwise, the state that you're constructing doesn't have the correct mass as seen from the infinity. So you have to dress the system with, so at a highly excited state, which corresponds to the energy level corresponding to the black hole's mass, and then you have an ensemble. You have a conventional statistical mechanics ensemble of states in this quantum field theory. And the claim is that this is a good model for black hole microstates. Okay, so this is the sort of our main picture. And it is, so the crucial point, and this is, I think, the point that many previous attempts missed, and that's the reason why they run into these contradictions, is that it is not the vacuum of the quantum field theory with the stretched horizon that we are interested in. We are actually interested in the highly excited state, which corresponds to the mass of the black hole. Okay, and then you get two things immediately. One is that you get an ensemble of states. So possibly we can explain entropy of the black hole using this, and we do actually. And at a typical state in the Hilbert space is energy as the mass of the black hole. And these excitations work as a model for the radiation that Israel and Mukoyama had as an ad hoc fix for this Boole-Ware vacuum problem. Okay, so this is our setup, and yeah, so this is the sort of the analog of fixing the energy or the temperature of the Planck ensemble. So black body, you take the look. Typically, we look at it at finite temperature, but you can also look at it at finite energy. Oops, sorry. And this gives you a definition of an ensemble, and it determines the energy and the temperature exactly. So the point of this is that the area scaling of entropy. So what we find, and this is kind of answering Sachin's question, which is that the scaling of the entropy is a direct result of there is a degeneracy in the angular directions in the quantum numbers that we find. So if you do a quantum field theory with this boundary condition, we can compute its normal modes, just like Planck did for the normal modes of a photon gas in a box. So you can do the same sort of thing here, and then what you find is that the normal modes are not those of the simple harmonic oscillator. What they are instead, I mean, they are so along the so in Planck's calculation, the quantum numbers, there is an nx, ny, and an nz coming from the three spatial directions, and that's crucial for the volume law of entropy to emerge. So what we find is that when we put this cutoff and compute the normal modes in the direction along the surface of the black hole, basically the dependence of the modes on that is extremely suppressed. So there is an almost quasi degeneracy along the angular directions of the black hole, which basically is what is responsible ultimately for the fact that you don't get this nx, ny, nz, but you get one direction less, basically, and that leads to this, instead of the volume law, you basically end up finding area law. So this is, this last fact, even though it is not phrased in terms of normal modes, is implicit in this old paper of Toft. So he also found an area law, even though it is not, I don't think he did not compute the actual normal modes of the system, but he found that the calculation results in an area law. So we are kind of giving it a mechanical understanding of it in some sense. That's not completely clear to me. So I don't know how to think about the localization properties of the states, because that's like, I think, yeah, I mean, we are thinking about it, but yeah, I mean, I want to say yes, but I'm not sure. It's the status quo right now. So, but yeah, I suspect they are. I suspect they are. So there is a, yeah, so, and associated to this thing, so of course, I mean, we have not really solved quantum gravity in any sense. What we have done is we have put in a parameter, which is basically the location of the stressed horizon. And what it basically is giving us is there is an ignorance in the location of the stressed horizon, which is, you can think of as a one parameter freedom. So it turns out that all the arbitrariness that we have in this calculation, all the things that we do not know about the calculation, they can all be contained into just this one parameter degree of freedom. And once you pick this parameter, so that the entropy of the black hole, entropy comes with an area scaling, but the precise coefficient is not fixed, because we are not able to, this stressed horizon location is an ad hoc thing for us. So, but once you pick that choice, everything else in the calculation is completely fixed, including the Hawking temperature comes out with the precise numerical coefficient correctly. So this is something, again, was not really there in Toft's old calculation. Now, also the Toft's calculation, I want to kind of distinguish myself from Toft's calculation, because he was not trying to understand what the states were. He was just making the statement that if you put this cutoff and you do a semi-classical mode, semi-classical calculation, not mode calculation, you would find area scaling. But there was no real explanation for what the states are one looking at, etc., etc. So, but what we are doing here is that we are explicitly looking at this, a very honest to God, like a very conventional system. There is a quantum field theory with some particular boundary conditions, one in the asymptotic region near the boundary of ADS and one near the stretched horizon. Then you get these normal modes, and we do the Planck-like second quantization. That's what we're doing. So, yeah. So the fact that both entropy and temperature can be obtained correctly encourages us to compute the correlation functions. And this is sort of the main point. And I'll kind of go through how much time do I have?
10 minutes for 15 minutes.
Oh, I see. Okay, I'm good. Okay, yeah, good. Thanks. So, yeah. So I'll, so far, like I have just tried to outline the story here. I mean, there are many papers I'm summarizing. So there is not, like in the next few slides, I'll give some equations, but not too many. So the point is that with these two things, we can fix both the entropy and temperature. And because of that, we are encouraged to compute correlation functions, because this looks like it's a genuine, at least it's a good model for the statistical mechanics of black holes. So let's try to compute correlation functions and see how do they look? Do they look like the smooth horizon correlators that one is familiar from? familiar with in standard classical quantum field theory done in the background of a black hole with a smooth horizon. So this is what we'll do. So we'll quantize fields with Dirichlet boundary conditions. These and then we'll consider typical excited states at energy equal to the mass of the black hole, and these states will be our models for our black hole microstates. Okay. So and then so there are various things one can do. So this extrapolate. There's ways of computing correlation functions in ADS-CVD. There are some standard technology which we will do. And the final point in some sense is that if you take the stretched horizon, once we compute the correlation functions and then take the stretched horizon towards the horizon, in the sense that the cutoff length, epsilon or whatever you want to call it, once you send it to 0, you find that the correlators precisely become what are called the Hartle-Hawking correlators, which are supposed to be a signature of a smooth horizon. Okay, so this is sort of the second part of the talk. So so the key idea is that this Hartle-Hawking correlator, as I said, it's basically, if you do quantum field theory in the background of a smooth horizon black hole, you put in appropriate smooth boundary conditions or infalling and outgoing boundary conditions at the black hole horizon, and this correlator. So this Hartle-Hawking correlator is usually viewed as an indicator of smoothness, in the sense that the boundary conditions at the horizon, in order to get these, are appropriately smooth at the horizon, and so this is considered to be an indicator of the principle of equivalence. So because the Hartle-Hawking correlator is an immediate consequence of smoothness in Kruskal coordinates, Kruskal is basically the maximally extended black hole geometry. I mean, it doesn't matter. So the fact that the Hartle-Hawking correlator is thermal. I'm giving you some reasons why people believe that Hartle-Hawking correlator is an indicator of smoothness of the horizon. And since we are able to reproduce Hartle-Hawking correlator, the claim would be that at least there are indications of smoothness in our calculation. So you can ask what really smoothness really means in this setting. So, so that maybe we can talk at the end. So, slightly more explicitly. So now I'm going to write a few equations, but not too many. So we are going to work with BTC, and this again comes back to TRG's question. So even in the BTC black hole, there are versions of the information paradox. So BTC is a black hole in 3 dimensions in ADS, where the cosmological constant is negative. And the major advantage, we can do very similar things actually in other black holes as well. So the main technical advantage in BTC is that the wave equations are exactly solvable in terms of hypergeometric functions. In higher dimensions, even in flat space, in flat dimensional, flat Schwarzschild black holes in 3+1 dimensions, the wave equations are writable, but they're not solvable. So strangely, the BTC black hole in 3 dimensions, the negative cosmological constant, is actually an easier system to solve technically than Schwarzschild. So that's one major reason why BTC is useful, because you can work with hypergeometric functions, which are real solutions of it. So anyway, so the boundary condition that we impose, this RH is basically the horizon location, and phi is some scalar, if you Fourier expand your scalar field in some modes, and you are going to demand this boundary condition at some small distance away from the horizon. So this is what our boundary condition is. And I want to emphasize that at the end of the day, the precise boundary condition here is not very important, as long as it is not dissipated. Okay, so this is, it can be Neumann, it can be, which one? This one. No, this is actually Dirichlet. So I'm saying that the field vanishes.
No. Expand it.
The
epsilon. The first power will be derivative. First value at the boundary.
See, but I'm not trying to interpret this as a statement around RH, right? I am trying to say that the function vanishes at this particular location outside the horizon.
So if you expand it,
Yeah.
and keep it up to order epsilon, you have 2 terms. The 2 terms
See,
are exactly what you will put as a condition for Robin.
but see the point, so I think you're trying to interpret that as a statement about this statement as a statement around the horizon. That is not what I want to do, because epsilon will have a huge significance for me. Because even though it is very close to the horizon, the physics crucially depends on epsilon. Yeah.
That will be coming in the length of Planck length or some other.
Sure, yeah. Right, yeah.
That's a way of regulating the theory using that kind of scale.
Right.
But effectively, you're considering it is close to, let's say, Robin Board.
I don't know what close means. That's the reason why I don't want to agree so quickly. Yeah, so the point is, but if you want to really say this, I have to expand it to all orders, right? So, and even if all orders, what I really want, this epsilon is has non-perturbative significance in the sense that it's like, it's the, if you compute, for instance, correlation, it cannot be set to 0 immediately. Yeah, so if you set it to 0, then it is not really the same boundary condition. It's just, for instance, this boundary condition, where did it go? So here, so this boundary condition, when epsilon go into 0 limit, I cannot formulate the question, as you will see. So because of wave equations, I need some, time-like boundary on which the wave can be standing. Yeah.
That is a regulating scale which, for example, Tioft was struggling with, something like that.
But he was not trying to, okay, so like there are many things here. So he was not trying to compute normal modes. He was, yeah.
But effectively, you wanted some kind of regulator which will tell him.
True. Yeah, but I don't know. I think that
Epsilon is what he had.
he had an. So I'm just saying that I don't want to commit to the statement that this is anything like a the Robin boundary condition, because that I'm not sure that, like, that makes me worried. So maybe we can discuss it, and yeah. So because this is what I'm demanding, like operationally, is just a standing wave at the cutoff. That's what I'm demanding. So, and the wave has to have a node at that location. So that's crucial for it. So maybe there is a way of interpreting it in terms of this thing, etc. But yeah. So anyway, so the point is that once you have this, you have a scalar field, and I'm quantizing my modes. I can find the scalar field and the standing waves and so on. And determining these normal modes is actually quite difficult. But in the regime that we are interested in, we can basically find some approximate formulas. You don't have to pay attention to it. The thing that matters here actually is that this function, this J, the dependence on J is actually somewhat weak, is quite weak compared to the dependence on N. So N is like your principal quantum number, and J is your angular quantum number. And so this is what I was saying earlier, that, unlike in the case of the harmonic oscillator or the standard Planck's calculation, the two quantum numbers would both be linearly dependent in the case of Planck's calculation. But here that is not the case. The J dependence, I have shown it here, but you can actually argue that in the regime that we are interested in, this dependence is actually exponentially weaker than the dependence on N. Okay, so essentially this omega Nj is only a function of N, and there is effectively a degeneracy in J. Okay, so this makes the calculation different fundamentally from the one in, let's say, flat space and in Planck's calculation. So yeah, I can draw. Okay, so let me not draw the plots. So so the point is, yeah. So this is so yeah. With these things, we can compute. We can write down the modes of the scalar field. We know what explicitly the normal modes are, and then we write down the modes. This is just usual quantum field theory where you're expanding in creation annihilation operators, with this UNJs being the modes of the wave equation, and the omega NJs are explicitly known, at least in the regime that we are interested in. And this is our quantum field, okay, expanded in modes like usual. And the vacuum that we are interested in, which is sort of the analog of the stretched horizon, of the Boole-Ware vacuum, but with the stretched horizon, is the place where all these annihilation operators annihilate this state, and this is what we call the stretched horizon vacuum. But what we are interested in, as I was saying earlier, is not the vacuum in the stretched horizon construction itself, but we are interested in a state that is at the mass of the black hole. Because if you look at this object, its mass, this doesn't have a well-defined mass, basically speaking. So this object, on the other hand, this is the analog of dressing the stretched horizon with radiation fluid, like Israel and Mukayama were doing, but we have an explicit way of implementing it using these excitations. This is basically the kind of second quantization that Planck would do in his case, and we are doing exactly the analogous thing. The only difference operationally is that the normal modes have a different dispersion relation. So note that everything is basically explicitly calculable, because we know what the normal modes are, and this is just ordinary quantization. And because the weak J dependence, the system is very similar to that of a free theory, except for this J dependence, which we can ignore. So because of the quasi-degeneracy. So then we can compute the bulk, the Weightman correlation functions. Weightman correlation functions is 2-point functions in these theories, standard quantum field theory correlation functions. And so we are going to compute them on states which are at this energy level. Okay, so this is how we construct the Fock space of this theory. And then we compute we look at states at this energy, and then we compute 2-point functions in them. I mean, there is a lot of detail here, but I think the picture should be not too, it should be straightforward to follow. So you have, we are quantizing this system, we are computing its second quantized spectrum, and we are looking at correlation functions at an energy equal to the mass of the black hole. That's really what we are doing here. So work with a typical such eigenstate, and this is what we call a typical microstate. So because note that there is a huge degeneracy of such states. When you get to this high level, you have a huge degeneracy of state, and that's why we can compute its entropy, for instance. So it's the same reason why in Planck's calculation, if you look at a high temperature state, it has an entropy which scales as the volume. Similarly, here also we'll have an entropy, but that entropy scales to the area here, unlike in the case of this thing, which is what I didn't show you, but that you can show that. So so this is what we are doing. So we compute the Weightman function on this typical eigenstate. So this is the object. So now once we compute the correlation function, now we can consider the limit when epsilon is going to 0, which is basically the limit where the cutoff, this stressed horizon, is being sent to 0. And this is that turns out that this correlation function that you compute next, so that we computed, is precisely the Hartle-Hawking correlator in the limit when epsilon goes to 0. And various nice things happen. I mean, I'm not showing you the results. I mean, but you can believe. So and you end up getting the smooth horizon correlator. So one of the advantages, so if you start with one of the manifestations of the information paradox, is that if you start with the smooth horizon boundary condition and compute correlation functions, you get the Hartle-Hawking correlator, but it has this fundamental problem that the correlator dies off exponentially in time. Okay, and such exponential decay in time for arbitrarily long times is an indicator of the information paradox. And the reason is that if you have any general thermal system, if you perturb it, it will relax for a while, but after that it has to show oscillations coming from the noise in the system. Okay, so in the case of a black hole, on the other hand, this is not the case. Because your boundary conditions are ingoing, you compute this correlation function, it keeps decaying forever in arbitrarily late times, and that means that there is, you never catch up with the fluctuations in the system. So this is considered to be a version of the information paradox, not quite Hawking's information paradox, but it's called Maldaceno's information paradox, but they are closely related and can be viewed as variants of each other. So the point is that, but this calculation, what we have done on the other hand, because we always have a finite epsilon cutoff, we can show that even though at the, when the corrections from the Hartle-Hawking correlator are exponentially suppressed in the entropy, those corrections, once the time gets to an order, or the time scale gets to close to that of the entropy, so order S time scales. Sometimes it is called the page time. So when the time scale gets close to the page time, this the leading coefficient, let me just write it. So we have a correlation function that we are computing, which is so you have a correlation function, and this basically looks like the thermal correlator, or I think it is my phone, maybe. Might be my phone. Oh, I think it is mine. So, I mean, okay, I don't know what to, so I'll have to figure it out now. So, no, I don't need to. I don't think it is. It's as usual. It is somebody trying to sell me a car. So, so this is what this is. So this is what you expect if you compute it in a heavy state. So let me call this a heavy state. So heavy state is, so if you compute light operator correlation functions in heavy states, you get a thermal result plus corrections which are exponentially suppressed in the entropy. This is a very standard fact which comes from, you can call it eigenstate thermalization, etc. if you want. But this is a fact that you expect. But if you work with the standard black hole with the smooth horizon correlator, you don't get this piece. What you get is you get exactly this. And that is actually a manifestation of the information paradox. But in our construction, explicitly this object is sitting there. Because of the fact that the cutoff is finite, this object is precisely e to the minus s by 2. So this is there. So which means that after a time scale of basically an entropy order s time scale, this thing will die off, and the remainder is basically this guy. And we manifestly do not violate the information paradox. But sort of this was what the entire point in some sense was. Because if you don't at least get this, there is no point in putting the stressed horizon, because the reason why we put the stressed horizon is to manifestly not violate unitarity. So, but we do get that. So, but the point in some sense is that, but we also are able to get this the smooth horizon correlator at least up to the page time. Okay, so there is a natural sense in which you can see in what limit this gives rise to the principle of equivalence, which is what we see in general relativity.
This here calculation you are doing in the CFT, right?
No, this is in the bulk quantum field theory. Yeah, it's motivated by the CFT, because see, the thing is, from the ADS CFT correspondence, we sort of know that the information paradox should have a resolution. So this is the sense in which string theorists have declared victory on information paradox. Oh, it's solved, But the point is that we still don't know what exactly is wrong with Hawking's calculation in the bulk. By bulk, I mean in the gravitational description. So we have a statement that, okay, this gravitational description is dual to a CFT, and the CFT is manifestly unitary. So of course, information has to come out somehow. But the question that we don't really know the answer is, how does Hawking's calculation fail? Because that's a gravity question. And that's what this is about. This is basically, we are doing a calculation in the bulk.
So basically QFT in curved space.
Exactly. So the QFT in curved space-time with some strange boundary condition. That's what we are really doing. And when we do that, what we find is that you get correlation functions which are indistinguishable from that of the smooth horizon up to the page time. So that's the sort of the punchline. So
Calculation is in the BTC background.
that's right. That's right. So yeah, so it's in the BTC background. So the point is that, we can show that the degeneracy in the spectrum is a very universal property of, for instance, horizons. So in the end, BTC is not very important, but BTC is where everything can be done very, very explicitly. So, but yeah. So, right. So so these are, let me just maybe skip this. This is kind of related to some recent developments that, there's going on. So there is a natural vein which connects with some of the things that, let me skip this also. So so let me come here. So right. So let me sort of conclude in a way. So by talking about how our calculation is different from Toeft's calculation and how it improves upon it, because I think I feel most like I'm plagiarizing from Toeft. So I have to defend myself in some way. Yes. So I mean, so it's half plagiarism from Toeft and half plagiarism from Israel Mukoyama. So, and we put it in the context of ADS CFT just to make the string theorists happy. And I think we are, so that's where it is. So the point is that, so one major difference from his calculation is that we are computing explicit normal modes. And also he was not working with this dressed state where there is radiation in the system. At least he was not explicit about it. And in fact, there is reasons to think that he thought that was a fatal flaw because he departed from it later on. So, but Israel and Mukoyama's idea was that if you dress it, then this divergence in the stress tensor, the negative divergence can be compensated. So that's one difference, this explicit normal modes. And it's still, there's normal modes. I just gave you some formula, but it's quite difficult to compute. And we still have not understood all aspects of it. Luckily, but only the low-lying part of the spectrum seems necessary for doing the calculation. So we managed without understanding it completely. So summary of, so essentially Toeft's calculation is that, Toeft observed that there is a scalar field around a black hole basically has what is called an angular momentum barrier. So there is a potential and, so this is the asymptotic region. I'm drawing it for the flat space black hole. So there is a potential barrier and there is a bunch of modes which are trapped behind here. So you put a stretched horizon here, then this effectively becomes a potential well of this kind. So he can look at the states which are trapped here. Okay, Toeft didn't have the advantage of ADS back in the day. So this angular momentum barrier was crucial for him. But now on the other hand, like if you are looking at ADS black holes, even the angular momentum barrier is not very important because the potential barrier roughly looks like this anyway. Okay, so you compute these normal modes. So what we are computing are basically these explicit normal modes. And so what he did was, he was very clever because computing normal modes is hard. So what he did instead was he used a semi-classical, Bohr-Sommerfeld type of argument to estimate, to do his calculations, and the price that he has to pay. So if you do not know the actual dispersion relation for the normal modes, what happens is that you cannot formulate it as just a standard ensemble calculation in statistical mechanics. The reason is that if you know the micro states in the theory, I mean the fluctuation modes in the theory, specifying energy specifies the ensemble completely for you, and all the other macroscopic quantities are calculable. But on the other hand, if you do not know the normal modes, you have to specify two things. So he had to specify both the mass of the black hole and the temperature of the black hole in order to get the area scaling. So in our calculation, for instance, we can just set m equal to some, whatever the mass is of the black hole, and then the temperature and entropy both we can compute. Okay, so that's one difference. So his modes were semi-classical, ours are genuinely tunneling modes, etc., etc. So, but that's sort of the major technical difference. So, and also I think that the entropy, why is it that the entropy scales with area is sort of demystified in this calculation? Because you explicitly see that the modes don't have a dependence on one of the quantum numbers. Okay, so that's the crucial difference between Planck's calculation and TÜV's calculation, our calculation, which is that in Planck's calculation, the modes depend on all spatial dimensions. There is an nx coming from one direction, ny from other, nz from another. But in the case of a black hole, when the cutoff is close enough to the horizon, one of these quantum numbers is suppressed because of the redshift of the horizon. And that's a very non-trivial fact, because without actually doing this calculation, I don't think it was easy to predict this, because we don't have an intuitive understanding why this is happening. But if you do the calculation, you find that that is the case. So anyway, so that's sort of so that gives you an intuitive understanding of the area law for black holes, which is usually considered to be not so easy to understand. So various questions one could ask, but these are all somewhat technical comments. So so maybe the main qualitative message. So so this may be the main point that I want to make, which is that principle of equivalence is an effective field theory statement. So just because you have a UV complete setting in which there is a cutoff around the horizon does not necessarily mean that in effective field theory the correlation functions are distinct from that of a smooth horizon, because you actually have to do the calculation to see it. And in this particular calculation, we find that the smoothness of the horizon, in the sense of the Hartle-Hawking correlator, is in fact, it remains. So our attitude is basically that the stretched horizon is a UV regulator. It is a finite n effect. Finite n means finite g Newton, and it's best to call it a quantum horizon, in the sense that it really captures the quantumness of gravity. So we are putting it at a finite Planck length. So if it has to be, well, not necessarily, it can be a few orders of Planck length, but the Planck length has to be finite in the calculation for it to give the features that we expect from it. So yeah. Okay, so this also I'll skip. So I think I can stop here. Thank you very much for your time. Yeah.
Questions?
How do you recover the equivalence principle as we know to be a good idea in classical, the semi-classical or the actual classical?
You mean, what do you mean? So the way I am, so the only thing we are really getting is that, see, usually the Hartle-Hawking correlator is viewed as an indicator of principle of equivalence in the quantum field theory curved space-time setting. So we are saying that we can reproduce that. So there is a second question one could ask, which is a more dramatic question in some sense, which is that what happens to somebody that falls into the black hole? What should he see or experience? This is a much harder question. Even if you just want to formulate an ADS-CFT, you have to have this is an observer. So you have to frame a question about an observer in a gravitating system as he goes through this thing. This might be like, we may not be ready for it. So one thing I will say is that I suspect that, like in the case, one of the surprising things about holography originally came from various ideas of this kind, like having horizons, membrane paradigm, like as was said, etc., etc. So the idea is that, like, you have a stretched horizon that is outside the black hole, but its dynamics can act as a proxy for the interior. So this would be sort of the hope, because we know that this is not impossible, even though it is quite dramatic, because we know that in the case of ADS-CFT, the CFT is living on the boundary, but it seems to be able to, capture physics by creating something like an extra radial direction. So this is something that we know in the case of ADS-CFT. But here, on the other hand, I mean, that's just a hope. I concede that point, which is basically that you have a surface but where the dynamics of that surface as somebody goes in. So we are trying to do a black hole complementarity type calculation, but it is quite hard. So we don't know whether we will succeed yet. So, but the point is that, like, so the only thing I'll say is that the Hartle-Hawking correlator is supposedly an indicator of smooth horizon, and it is not supposed to have come out from the calculation of the type I did. Because if you put a cutoff, you immediately get some other correlator. But by viewing the state as an excited state on the stretched horizon, we immediately see that that problem is not there. So that's sort of the punchline. So at least it's going in the right direction, even though a complete answer to your question is, yeah, it's still hopefully in the future. Yes.
So I guess you chose a particular dimensionality to spend most of your time on.
Yeah.
And I'm assuming that the reason the other dimensions don't matter is that eventually the redshifting happens normal to the horizon, and that's what matters. So
that's right. Yeah.
The number of dimensions doesn't.
That's right. So conceptually, that's exactly the point. So we expect that. So the technical reason why we focused on BTC is because the wave equation is exactly solvable. So, in higher dimensions also, in any situation, in fact, whenever there is an horizon, if you put a cutoff right in front of it and compute normal modes, we can show that there is an approximate quasi-degeneracy of in the direction transverse to the radial direction. So this one can show. So in that sense, we expect the physics to remain intact in some. But of course, there are various details one will have to be careful about. But I don't think there is a conceptual issue there.
And the heavy state that you mentioned,
Yeah.
just a highly excited state of the.
That's right. So in the CFT side, yeah. So that's a good question. So in the CFT side, the black hole is viewed as a state whose energy scales with this n that I was talking about. N is like 1/g Newton. So that means, so in order to model that in the bulk, so that also ties in naturally. That's sort of another way of saying it, which is that, this idea of dressing the stretched horizon with radiation fluid. What we have done is that we just said that, okay, you have a stretched horizon quantum field theory. You're supposed to look at states at energy equal to, or the mass equal to the black hole's mass. So that mass is, again, it's like, that effectively means that, the associated Schwarzschild radius is order 1. So so G times M is order 1. That's what the Schwarzschild radius is. Schwarzschild radius is, if it is not order 1, the system is not backreacting enough. It's like a small fluctuation. But if G times M is order 1, it means that M is scaling with N, right? With G times, so M is scaling with 1/G. So that's precisely the kind of thing that you would want from the CFT as well. So that also ties in some way, yeah.